GPS, show you how GPS works and everything. And then the other thing I wanted to cover after that was I'll talk about it. I didn't skip around. Alright, so let's see what we can do here. Sure, I'm going to have to do something. Click on something. Let's have to click on something. Chapter 5 is naming. How we do naming across the distributed system. I'm not going to spend too much time on Chapter 5, because I really want to get to coordination, which is the interesting one. Hey, it worked. That little thing on the bottom. The light gives me the screen that's not like the full screen. Right. So I haven't even downloaded Chapter 5 slides yet. So maybe we'll just do 4 tonight. We'll start 5, go over the homework, and review for the midterm, which will just be like the first 2 homeworks. So, but if you go ahead to Chapter 6, coordination, that's the thing that I'll spend the most time on. And then one other thing after that. So we're almost done, actually. 5 is naming. We talk about things, symbolic things. Back in the old days, we had a distributed file system. Talked about communication. There's transient, persistent, and asynchronous and synchronous. I think we talked about that last time, but I'll just review it again. There's places for synchronization at request submission, at request delivery, and after request processing. Now, client-server computing is generally based on a model of transient synchronous communication. Client-server have to be active at the time of communication. Client issues a request and blocks until it receives it. Server essentially waits only for incoming requests and subsequent processing. Now, the drawback is client can't do any of the work when he's blocked. So then there's message-oriented middleware, which aims at persistent asynchronous communication. But they're queued, like email. If you're not logged in, your email doesn't go away, right? That would be terrible. Communication between caller and callee can be hidden using a procedure call mechanism. We talked about this last time. Is how stubs work on both sides. It looks like you're calling a procedure, but it's really turned into a message to send to the other guy. And the other guy assembles it and actually does the procedure call and then returns the values. And the problem is you could have different data representation. And complex data values like arrays and unions have to be copy in and copy out. All data has to be operated on as passed by parameters. It excludes passing references, because the address on my machine has nothing to do with the address on your machine. So if I'm passing an array, full access transparency cannot be realized. If I'm passing an array, I have to copy the whole array and send it to you, because you're on a different machine. A remote reference mechanism enhances access transparency. Remote reference offers unified access to data. Remote references can be passed as parameters and RPCs. It's sometimes now, one of the problems is when you might have distributed memory, which he doesn't like. I saw in one of the early ones. But there was a time when Professor Whitlock was telling me that IBM was talking about near and far memory references. Near was on your own machine, your own local memory. Far was on somebody else's machine. And IBM was pushing NUMA, non-unified memory access. But I remember in one of the earliest slides, I forget where, he said, nah, they don't do that anymore. Not a good idea. So talked about sending out multiple RPCs. Here's how it works. Practice. Talked about it. Compiler. This is, I remember, IDL compiler would be, I forget what IDL stands for, but that was, they sent me to this 2-day education seminar in the city to learn Corba, which I didn't like, that was part of it. Client to server binding. The client must locate the server machine, and 2, locate the server. So he looks at the directory server, finds this DCE daemon, request support, blah, blah, blah. Ask for a port, and then do the RPC. Talked about sockets, Berkeley socket interface. Create a new socket, bind. Somebody asked what bind was last time. Bind means binding a port to a socket. So if I'm a server, and I like in Java with this, to show the asymmetry. There are server socket objects which can spawn multiple sockets, and there are client sockets. In order to connect to me, if I'm a server socket, you need my IP address and you need a port number. It's not a physical port on the computer, USB port, serial port. It's a symbolic number, like port 80 is for web, for the web server, HTTP. So, bind registers a port for that socket. So when you try to make a connection, when network traffic comes in for that port, your program, in this case the socket, with the socket, is registered for that port, like send me that stuff. Okay? And you tell the operating system that the maximum number of pending connection requests should be, and block the caller until a connection request arrives, and then actively attempt to establish a connection. To send, receive, and close. So you can have multiple connections. There's the server and the client. I just like the server socket. You can look up, I think you should look up, ignore this in Google, how sockets work in Java. The server socket object and the socket object. It's a lot easier. You don't need all these different calls. It encapsulates all of them. It encapsulates the first few calls in the constructor for the server socket object. And every time somebody tries to connect to you, you spawn another socket to handle that connection, and then you go and listen for another connection. And normally what you do, at least what I did in the class, the undergraduate class, client server, reviewing, I forget what it's called, design and implementation one, whatever it was. I don't even think we have that anymore. I got rid of my client server web computer for that course. But in that course, we would spawn a separate thread. Every time a client connects, we create a separate thread to handle that connection. And the main thread would be listening for the next one. And that's what I did with the multi-threaded server as well. But that's what I had them do in the class. Then sockets are rather low level, so they have this thing 0FPQ. By pairing sockets, one for sending messages and a processor and corresponding one at Q for receiving messages. All communication is asynchronous. Three patterns are request, reply, publish, subscribe, and I don't want to go into too much of that. I never use that system. One thing that's going to come up is MPI, which I did use in that class use. OpenMP and MPI. And you can have a pipeline. Here's a worker. I have some code where I talk about how to handle multiple workers and stuff. Some stuff I wrote up, once again, notes. They're hard to read. I wrote them without part of the publishing. We'll go over those later. We're getting this out. Okay, so anyway, I don't care about pipelines. This is what we use. We also use MPI when lots of flexibility is needed. So MPI append an outgoing message to a local send buffer send, and then send the message and wait until copy to a local or remote buffer. There's another MPI, send the message and wait until transmission starts. The different ways you can do it. And then send and receive, send the message and wait for a reply, pass a reference to an outgoing message, continue, JSON, and then there's receive, and then there's a peek, check it for the incoming message to not block piracy. By the way, there is a socket operation they don't show with Berkeley sockets where you can peek in the socket, see if a message has arrived. Unlike the receive with the socket, which is blocking, it's not blocking. You just look, is there a message for me? If not, go about my business. Okay? I forget what it is. You have to Google it. I don't care. I'm just letting you know that that functionality exists. So, now, asynchronous persistent communication through the support of middleware level queues. Queues correspond to buffers at communication servers. So some of the operations are append a message to a specified queue, get, block until a specified queue is not empty, and remove the first message. Hold, check the specified queue for messages and remove the first, but never block. And notify, install a handler to be called when a message is put into the specified queue. So there are queues. Queues are managed by queue managers. An application can put messages only into a local queue. Getting a message is possible by extracting it from a local queue only. Queue managers need to route messages, so here's an example of routing. By the way, I should mention, actually I shouldn't mention, let's just go over this thing. There's a source queue manager on the local OS. Look up the destination address of a queue manager. There's an address lookup database. Look up contact address of destination queue manager. Here's the logical queue level address name, the destination queue manager. And so you send it across to him. You have the contact address. So you're managing queues. But they're asynchronous because messages don't disappear if you don't have an immediate connection, like with a socket. If I try to make a socket connection and you're not listening, it's gone. Or if I'm sitting there with a socket listening for you and you never make a connection to me, you crash, then it's gone. It's transient. So now, a message queuing systems assume a common messaging protocol. All applications agree on a message format, the structure and data representation. The broker handles application heterogeneity. Well, heterogeneous, different. With the ITY at the end. I'm not pronouncing it correctly, I'm sorry. In an MQ, broker handles application heterogeneity. In an MQ system, transforms incoming messages to target format, very often acts as an application gateway, and may provide subject-based routing capabilities. For example, publish, subscribe capabilities. So there's the general architecture of a message broker. You have the application with the interface, a local OS. Here's the broker plugins and the rules. Okay, there's the message broker, and there's a destination. So to get from there to there, you send something to him. The broker figures out what to do, and then he forwards it onto the application. So you have a guy in the middle, a message broker. Also for remote procedure calls, with Corba, there's an object request broker, a middleman that handles all the remote object requests. So it's not just a procedure call, but accessing a remote object, method of a remote object. I didn't like Corba, but I see now with the IDL, that's common to Corba. I forget what that acronym stands for. Because Corba has that too, and it's just too much syntactic sugar. So it's just, we're going through the rest of that. Yeah, interface definition language. But it's kind of, I found the one for Corba where you define the client and the service stubs to be just kind of detailed. I like things that are simple and clean. I hated Corba, but Professor Macklin, I was doing some work for him. He was paying me over the summer, so I had to go to the city to this Corba educational seminar, and I really didn't like it. And I had a guy I went to school with, Wayne, who was doing Corba at the time, he was consulting, he loved it. I don't like stuff that's too complicated. I like simple. KISS, keep it simple, student. A lot of this stuff I'm showing out these slides is too complicated. It's too much syntactic sugar, in my opinion, anyway. So, and then we can talk about IBM's WebSphere, MQ. I don't really care. That's what they do. By the way, in terms of parallelism, like MPI and OpenMP would be things that we use. There are other, parallel threads, pthreads. Also, I think this Hadoop was Google's language of parallelism, right? Now I have to look that up too, Hadoop. Apache Hadoop. Look it up. Apache's website. Is a collection of open source software utilities that facilitate using a network of many computers to solve problems involving massive amounts of data and computation. It provides a software for, all right, you can look up Hadoop. That's what Google was using. It's another way of doing parallelism on a distributed network. Okay. All right, so what does IBM WebSpace Sphere MQ look like? This is what it looks like. You can look at it. There's a sending client and a receiving client. They both use stubs. Channels are inherently unidirectional, automatically start MCA, automatically survive. Any network with few managers can be created. Routes are set up manually by systems administration. Not interested in that message channel. Right. So you can also read about that later. Now, what about application level multicasting? Multicasting is when you want to send a message to a lot of people. So you organize the nodes of a distributed network into an overlay network and use that network to disseminate data. All right, now here's something that is worth talking about. You understand what an overlay network is. The physical network is just the Ethernet cables, the wires that are connecting things. An overlay network is something you impose on top of that. Maybe I'm connected to you and you're connected to her, but in the overlay network, we're directly connected. You know the message has to go back. Or it might be, some kind of network, and we just connect everybody in a circle. Okay? So, you organize the nodes of a distributed system into an overlay network and use that network to disseminate data. Sometimes, oftentimes, I didn't even know that was one word, oftentimes, back in the 1800s, 1700s, oftentimes a tree leading to unique paths. Alternatively, you also have mesh networks, which require a form of routing. Now, one of the simple overlay networks, and that's why I gave you a problem on the second homework in the hypercube, is just to organize it as a hypercube. Okay, now, how does basic level multipassing in a chord? Remember, chord is circular with keys are numbered, and every node is responsible for all the keys that have a lower number than him that's above the other number. Go back and look at the picture of the circle table. Sometimes connections across the circle of life. All right? Go back. Should I go back to the chord, chapter 3, to show you what it looks like? Gosh, we'll do that. Go back. I think it's in chapter 3. Find the chord. Might be chapter 2. Yeah, I think it's in chapter 2. Oh man, I opened the wrong one. Alright, forget this. Chapter 2. I want to take it early today. Now I can't. Just tell me when you see a big circle. That's the chord. It's the hypercube. It's There it is. It's a circle. This guy, actual node, is responsible for all these guys that come after this guy. I'm responsible for everybody less than me, number less than me, or in the circle that's above the previous guy. So like 1 is responsible for 2 and 3. 4 is responsible for 5, 6, 7, 8. But we also have shortcuts across the chord, like a web. Like, I think I used the example of Dreamcatcher. Stupid Stephen King book. So that you can have the idea of what a chord is. So the initiator generates a multicast identifier, MID, M-I-D. He looks up the successor of the multicast identifier, the node responsible for it. Request is routed to the successor of the MID, which will become the root. If P wants to join, it sends a join request to the root. When the request arrives at Q, if Q has not seen a join request before, it becomes a forwarder. Who P becomes a child of Q. The join request continues to be forwarded. Q knows about the tree. P becomes a child of Q. P becomes a child of Q. No need to forward join requests anymore. So, if he's not seen a join request before, he just forwards it. If he knows about the tree, he doesn't have to forward it. So there's an example. So some cost, link stress. How often does an ALM message cross the same physical link? For example, a message from A to D needs to cross R sub A and R sub B twice. There's also stretch. A ratio in delay between an ALM level path and network level path. For example, messages from B to C follow the path. Okay, so look. It's application level multicasting. That's ALM. So sometimes there's problems. Link stresses, sometimes it has to cross the same physical link. There's stretch. Sometimes the ratio of delay between the AML and ALM level path and the network level path. Remember, it's a, come on, help me out here. What's the word I'm using? It's an overlay network. So again, if I keep sending you a message, you send one back to me, he's going to have to see it twice, even though we're not interested in telling him anything. I don't want to tell him anything. You understand? So that's what we're talking about here. And maybe there's more of a delay. If there is a direct connection, and I could send messages directly, that would be faster than the overlay. Whatever. So then flooding is another way of doing it. P simply sends a message out to each of its neighbors. Each neighbor will forward that message except to P, and only if it had not seen the message before. The more messages, the more edges, the more expensive. So that's just like, I have a message I forward to all my neighbors. He gets the message, he forwards to all his neighbors except for me. Unless he's already seen the message. Right? You know, it's like when you're doing a search or a graph. If you've already visited that node, you don't visit it again. Follow? I'm not explaining this stuff very well. Let Q forward a message with a certain probability, possibly even dependent on its own number of neighbors, its node degree, or the degree of its neighbors. Assume there are no write-write conflicts. Update operations are performed at a single server. These are epidemic protocols. That's a good name. A replica updated state to only a few neighbors. Update propagation is lazy, not immediate. Eventually, each update should reach each replica. Update propagation is lazy. Eventually, each update should reach every replica, not immediately. So if I update something, I gotta tell everybody else about it. You know, single server does the update. A replica passes updated state to only a few neighbors. Update propagation is lazy, it's not immediate. Eventually, each update should reach every replica. Now, there's two forms of epidemics. Anti-entropy. Each replica regularly chooses another replica at random and exchanges state differences, leading to identical states at both afterwards. So, okay. And then there's rumor spreading. A replica which has just been updated has been contaminated. It tells a number of other replicas about its update, contaminating them as well. So the first one is just, you talk about the differences. You're only telling the differences, not the whole replica. So the principal operations of anti-entropy. A node P selects another node Q from the system at random. Pull, P only pulls in new updates from Q. Push, P only pushes its update to Q. Push-pull, P and Q send updates to each other. For push-pull, it takes order log n rounds to disseminate updates to all n nodes. A round is when every node has taken the initiative to start an exchange. So it takes time. I don't want to go. The analysis is how long staying ignorant, push, pull. I don't care about the time it takes. It's the anti-entropy performance. And rumor spreading. The server, as having an update to report, contacts other servers. If the server is contacted to which the update has already propagated, S stops contacting other servers with probability P stop. Okay. The observation. If S is the fraction of ignorant servers, i.e. servers which are unaware of the update, it can be shown that with many servers, that's basically the fraction, e to the minus 1 over whatever. It's always e. E comes up in probability theory all the time. E is the base of the natural logarithm. It's about 2.71. You know, if you have a bank, I'll tell you another definition of E. If you have a bank balance of $1, and you give me 100% annual interest, after 1 year I have $2. If I compound it monthly, I'm going to have more than $2. If I compound it daily, I'm going to have a lot more than $2. If I compound it every second, or if I compound it every nanosecond, what's the limit? I'll never have more than $E, which is about 2.7. If it was compounded continuously. I knew that because that was an approximation I used to do. I should pay you for $2. Well, I knew the other people. Anyway, so here's the wrap up. So let us note the fraction of nodes that have not been updated susceptible. The fraction of updated infected and active nodes are the fraction of updated nodes that gave up. They were removed. theory of epidemics, this is all the rates of change. The rate of change of the updated nodes with respect to time is minus s. The rate of change of the infected nodes with respect to time is that, and so on and so on. There's a whole, I don't really care about the probabilities. I have a friend we know from high school. Well, friends of friends I went to high school with. Really nice guy. Charlie DiMaggio. No relation to DiMaggio. He was a professor at Columbia, and he became a professor later in life. He's smart. He was a medic for a long time at Elmhurst General Hospital, and then he got his PhD in epidemiology, and he became a professor at Columbia of epidemiology. Then he moved to NYU, so he knows all about epidemiology. They always contact him, like for the New York Times, like, interview him for the New York Times, like for COVID, and then later on for gun control. He knows a lot about all this stuff. So, but he's still a nice guy. So he studies epidemiology. I don't, so I don't really care. And there's the effect of stopping. So anyway, if we really have to ensure that all servers are eventually updated, rumor spreading alone is not enough. The fundamental problem, we cannot remove an old value from the server and expect to remove it to propagate. Instead, mere removal will be undone in due time using epidemic algorithms. The solution, removal has to be registered as a special update by inserting a death certificate. Alright, enough of this. It's too grim. Once you remove a death certificate, it's not allowed to stay forever. Run a global algorithm to detect whether the removal is known everywhere, and then collect the death certificates. It's like garbage collection. Assume death certificates propagate in finite time, associated maximum lifetime for a certificate. Can be done at risk of not reaching all servers. It's necessary that a removal actually reaches all servers. So that's it. I don't really know about that. It's too complicated, all sorts of things. But the idea is, how do you send a message to everybody? There's different strategies. You don't want to overload the network. So you want to do a little at a time. And they use the analogy of the disease spread. Then they have all kinds of those formulas. My friend Charlie DiMaggio knows all about them. I understand them, so I'm just not be on the scope of what I want to talk about. And so those are a couple of ways of disseminating messages. That multicasting, where you want to send a message to everybody. I update some important thing, call it a replica. Okay, so here's an application. Before I end, I want to just give you the idea of what's going on. Then you can start reading chapter 5 next time. I'm not going to spend a lot of time on chapter 5. Chapter 6 is where we're really going to focus on next big attention. Naming conventions. But here's the idea. You have a website, but you want it replicated at servers all around the world, so that if you want to load that website, you can load it from the closest server to you. If you're in Germany, you load it from that server that's in Poland, right? Because you're right there. So Germany and Poland aren't that close. I guess Germany is. If you're in Oregon, you can load it from a server from Seattle or from California. If you're in New York, you can load the web page from the replicated server that's in Chicago, Pennsylvania, whatever. The point is, if I update the page, update one of the replicas, I have to broadcast or multicast that to everybody else who has a copy, who has a replica, a copy of that page. So that's what they're talking about. How do I get that information out there to all of them? Sometimes I only have to tell them, look at my neighbor, what his replica is, and only tell them the specific difference. Just change these two lines. Other times I want to send the whole thing to everybody. Kind of like in a tree, fans out. Okay, and then these other methods are just like they came up with these methods trying to analyze, make it analogous to how disease spreads. And it's too depressing. It's funny, I was talking about science fiction that I like to do in class, and I was talking about time travel stories. And one was Connie Willis's great book, but it's very depressing. The Doomsday Book, where they travel back in time to observe things. Most of our novels about it, they're observing the London Blitz in World War II. But in this time, she travels back to the Black Plague, and she can't get back because something is happening in the future that prevents her from getting back. So she has to live with knowledge, to try to assist people in their suffering during the Black Plague. It's really depressing. But it's really well researched. Got great music from the New York Times. The whole Doomsday Book. It's a great book, but I wouldn't necessarily recommend it. It's kind of depressing. Then later on, Lincoln Streams. But later on, she has fun novels like Bellwether, To Say Nothing of the Dog. So, but Connie Willis is the single. I mention her because I really like her short stories. She's the single most honored science fiction writer in history. She's won more Hugos and Nebulas. Double Canada Awards, everybody else. She's a great writer. She's always been alive, I'm sure. So, but that's what that reminded me of. We talk about epidemics, the Black Plague. Not very funny. And it was, why do you think they're always worried about the flu and where you get flu shots? Because they were always afraid that it'll happen again. What happened in World War I? The flu epidemic that killed several million people worldwide. Killed 1 out of 6 adults in some cities in the U.S. Their bodies were piled up. It was a bad flu. People's lungs were filling up with blood. You don't want to hear about this, do you? I'm sorry. I'll let it go. But that was a really bad flu. The flu pandemic. I think it's actually the worst pandemic in human history in terms of fatalities. Soldiers brought it back to the U.S. from World War I. And then there's this damn But that's enough. I'm not going to test you on most of the stuff in chapter 4. We'll zip through chapter 5 after doing a review for the midterm. But chapter 6 is the important one. Coordination.